Okay, so today, so the plan for today is first I'm going to give you the SPI modules of the light sensor. These are pretty simple, just sensing the light intensity, and it has an SPI communication ports. So directly plug into your IPGA, and it is able to send all the digital signals through SPI to your IPGA. Very convenient. And are there any other modules or digital modules you can think of are using SPI ports? Just haven't used them, right?
Yeah.
Okay, so the very last project in the 351 class, we use ESP32 to measure. So definitely do it. Okay, so we are not making a PCB out of it, but it's a very good experience to have. So ESP32 senses the data from the accelerometer. What's the port over there? That's the I2C port from the accelerometer to the ESP32. And the data is being logged into somewhere and also send it over wirelessly to another module. So the SD card, most of the time, the SD card modules are SPI ports. But the sensors like the one wire, the temperature sensor is very similar to I2C, but it's not I2C, just one wire. It's a totally different protocol developed by Dallas Semiconductors. And the accelerometer is totally just I2C. And the OLED display module is also I2C. So I2C has SDA, which is for data, and SDL for clock. Just two lines for I2C. It's two lines, so it's very simple to use, and also for programming. But the logic circuits inside the modules are very complicated. So whenever it's getting easy for using it, the design will be more complicated. But for SPI, it's a little bit more complex compared to UART, but simpler than I2C. If you look at the Verilog, it's not very long. Okay, the timing is slightly more complicated than UART. Okay, if you have to rank the complexity of the three most common, they are all serial. Okay, serial communication. So probably UART is the simplest, and SPI and 2C, and then USB. So these are the complexity level of these protocols. So we're going to use SPI because this guy has SPI inside. If I look at the module here, right? I'm going to give it to you right now. Here. One very quick question. Could you see the light sensor? It's a little LED, right? It's a photodiode instead of the LED. It's not emitting, it's receiving and convert the photocurrent into voltages. By the way, there's a very interesting project I want to work on for the senior sound teams in the future. So one of my classmates in graduate school, and he directly after his PhD study, he found a job in the company making CMOS imagers, just camera for a DoD project, Department of Defense. And after like 3 years, so he did his camera project with that company. And after finished the project, he went to another company making analog circuits, also IC level. But he still has all the design files for the camera. So we are trying to make a camera probably, I don't know when, we'll see. If it happens, probably I'll let you guys make a camera out of it using Cadence. So it has ADCs in there, and maybe you can start with like 60 by 60 number of pixels on the camera. It'll be something similar to this, just photodiodes, right? They're actually just the diodes, PN junctions. And put the PN junctions in there and hold it using capacitors, and then send everything out to the ADC to digitize it. And have to implement probably some of the digital ports onto the chip. to send out the data to, it can be FPGA, and then send it to monitor eventually. That can be a very good project. And so this is just a 1 pixel, right? Just 1 pixel. Just 1 pin junction, 1 pixel. Is that 1D? Maybe just 1D, 1 dimension, I think. Yeah, if you have a pixel array, it's going to be a two-dimensional layout. So my question is, where is the SPI digital block on the board or in any of the chips? Where is it? Could you tell if this is a 2-layer board or multiple layer board? It's a 2-layer board, just top and bottom, like the ones you made. Is it necessary to make a multi-layer board? You don't have like 1, 2, 3, 5 components on it. No, it's just 2-layer, the cheapest. Thicker, yeah. Since it's 2-layer. So my question is, where is the SPI? Where is the SPI? Good question, actually. I mean, I made a wrong statement. It's not 2-layer board. You know why? If you flip it, look at the back. Did you see the little tiny holes?
Yeah.
A few very tiny holes. Did you see the 2103? Did you see that number?
Yeah.
Did you see the very small holes? It's not a through hole, but it's a hole. There are holes, right? And the holes are not through holes, which means they are not 2-layer boards. It's not a 2-layer board. The hole get into the intermediate layer somewhere. And another reason I can tell it's not a 2-layer board is if you look at the pins for SDO, SCK, these pins, I couldn't even see the traces connected to SCK. Could you?
No.
Did you see a trace connect to SCK? No. Did you see it? I'm not seeing a trace connect to it. So it has to be routed in the intermediate layer somewhere, okay? So in that case, we are not able to tell, because we cannot see the traces. So where's the SPI module? Where is it? Yeah, I think so. So they didn't integrate anything to the photodiode. It's also a silicon wafer. It's a diode. Right? The diode is definitely not digital. It's just a diode. And I think the IC chip, the little tiny chip there, integrates. It has current to voltage converters, ADCs, and SPI in there.
In that little chip.
Yeah. So the photodiode has photocurrent being sent to that chip, and the chip senses the current and convert to voltage. So which means you need a TIA in there, transimpedance amplifier, op-amps. It's an inverting amplifier, but convert everything to voltage. And the voltage is analog, so I have to digitize it, right? I got a digital signal. You digitize it. If it's an 8-bit ADC, so we got an 8-bit digital data stored in the memory. And you want to communicate because this is SPI module, so it has to be an SPI port. Okay, but SPI is serial parallel port. Serial. No, it's not parallel. So parallel, it means you got all the 8 bits being sent out at the same time and received being received by can be a shift register like parallel in, parallel out. Okay, but how many pins do you have for the SPI? Just the SDO, SDK, just 2. So it's a serial communication. So the SDO is a data output, serial data output, SDO, sending out bit by bit and being clocked. Okay. Make sense?
Yeah.
You know, design a chip like that. It's a lot of things in there.
That's impressive.
Yeah. So I'm going to introduce SPI real quick, and after that, we're going to do the quiz on ethics, right? It's the same question that as the ones I sent it over the link on the PDF. So most of them are just common sense. You can directly use your judgment, right? Maybe.
Maybe we'll let the Google see.
So SPI has MOSI on both, you know. So there are actually totally four digital blocks, 4 digital blocks, 2 for each. So M means master, S means slave, but we don't want to use that word right now, even though it's still the name for the ports. But now we use follower and master, or leader. Sorry, so leader and follower, right? Leader and follower. So M is a leader, S is a follower. Okay. So MO means the leader out and follower in. And the user is the one who defines which one is the leader, which one is the follower. And so for MOSI, you need a MOSI digital module behind this wire inside the chip for the leader, and also you need an MOSI for the follower. So there are 2 digital blocks. They are different. There's a leader MOSI and there's a follower MOSI. Make sense? Okay, same for MSO. It's a master in, slave out. Okay. Same for this one. And this is just a clock, just one line. And these are also just a one wire, just 4 wires for SPI most of the time. You are not counting the VDD and ground. Okay, so 4 wires for SPI. Keep in mind, can be an interview question. How many wires for I2C? And what are they? SDA and SDL, just 2. Okay, that's why it's easier to use. It's more complicated in the design. SPI has 4. Okay, so these 2 are data lines. If the leader is a transmitter and the follower is the receiver, which line is doing the data transmission? If the leader is a transmitter and the follower is a receiver. No. I mean, you got only 2 data lines, right? If the leader is a transmitter and the follower is a receiver, which line is? Yeah, first one, right? Okay. And vice versa for the second one. Okay. And so SS with a bar on the top, it's a chip selection. You have to enable it with a 0. So you can do all the data transmission. It's an enable pin. And it's a 0 active, means because it has a bar on the top. So put a 0 in there, it's going to start doing all the job. Put a 1, you disable everything. Okay. Now, it sounds frustrating because we have to design 4 different digital blocks. 4 digital circuits, 1 here, 1 here, and 1 here, and 1 here. Okay. And this can be confusing for now. Let's get into the code first. One thing you need to know is for SPI, you can define like the length of the data. Doesn't like UART. It's usually just the bytes, byte by byte. It's sending 1 byte each time for UART, right? But for SPI, you can define the length of the data. Can be 8, can be 10, can be anything. And also the leader defines the frequency of the clock, SCK. So that clock frequency is defined by the leader. So the follower is not able to do that. That's the leader's job, right? What's the frequency of the clock on the FPGA board? 100 megahertz, right? It's too fast for a lot of peripherals, including the SPI module over here. So we need to divide it by 50 times. So we're using actually 2 megahertz, which is a pretty good or very popular frequency for SPI. So how to divide it by 50 times? How to get a 2 megahertz clock? So this is a code for that. Keep in mind, you're counting to a certain number because the goal is to make a 2 megahertz clock. All right, so 100 divided by 2, we're getting 50, right? So we're actually dividing the clock, original clock, by 50 times. So when you're designing that clock divider in your Verilog, you need to count to 25. It's 25, you flip it, right? 25, you flip it, and 25, you flip it again. So actually, you have to count it to 25 instead of 50 in order to make out a 2 megahertz. So further, to explain this a little bit further, see 50 cycles, and this is the frequency of 100 megahertz. Okay, I'm taking out 50 cycles in the 100 megahertz clock. Okay, just assuming we're doing that. This is just a one frame of the 100 megahertz clock, and there are 50 cycles in there, like 50 on 1 and zeros, 50 periods. And if you want to convert this part, this 50 cycles, into 2 megahertz, okay, should we count until 25 or 50 to flip the clock? While we are talking about flip, because this is what you can do in Verilog, right? See here, we are flipping it. That's what we can do based on the language we have available to us, right? Think about it. Slow down a little bit. I'll let you guys who answer this question for me. So the goal here is to make a 2 megahertz clock out of the 100 megahertz clock from the board. Okay. And we need to count it to 25 and then flip it. So the question is why? How do we understand that? So I'm giving you an example. I'm assuming this is a 100 megahertz clock here. And I'm taking out 50 cycles from that clock. Okay. I want to make a 2 megahertz clock from these 50 cycles. So I should flip it here first and flip it here again second to make a 2 megahertz clock. So that's why I have to count it to 25. Okay. So in that case, if you count to 25, you flip it, and then 25 again, flip it again, you are getting a 2 megahertz clock. So otherwise, if it's not reaching 25, just adding 1 to it, okay, until it reaches 25, flip it. So this is a very simple clock divider to divide it by 50 times. And always at negative edge of the clock or by SCK. So the SCK is the divided clock from the 100 megahertz, which is like 2 megahertz frequency we're using for the SPI. And now here's the question: why do we need a negative edge? It's a falling edge trigger. I'm going to explain that based on the timing here. So it's all set up by the user. we don't have to worry about right now. Okay, just in case we know that at the falling edge, this is defined by the code, right? You can change it. Nobody tells you like you have to do it. All right, just assuming that we have to do it at the falling edge of the 2 megahertz clock. And this is a follower receiver and leader transmitter. You can look at the name of it. It's SPI leader transmitter. So the leader is sending and the follower is receiving. So the code is very simple. We're not going to dig into details, but just look at the big picture of it, right? So at the very beginning of the state is ready, RDY is here. If the send command from the CPU is lighting the leader transmitter to send something out, so we want to change the state to start. And it's going to be busy, right? Set the flag to be busy. And the length is 8. So for the index, it's 0 to 7, right? So we want to make a 7 here, so the index starting from 7. We are storing data to bit 7 at the very beginning. And 0 to SS, because it's required, you got S as one of the pins, the enable pin for the SPI, which is here, right? So I'm going to put it down first to enable the transmission. The MOSI is just one data line, right? So you can directly send the data at data 7 MSP to MOSI, and then decrease that index, move to 6, and get into the transmit state. One quick question, all right? If index is 0, is it doing everything here or just doing the first line? Just the first one. If you want to do everything here, you have to use a begin and end to wrap it up in the if statement. That's the syntax of the Verilog. Can be a little bit confusing. Okay, keep in mind, it's just executing the first one inside the if statement. If the index is 0, which means all the data from 7 to 0 they already sent. They are already sent to MOSI. And not yet. You still have 0 here, right? You do 0 again. That's the very last one. And so if it's 0, actually change the state to stop. But at that moment, it's still 0. Okay, you still want to put 0 to this data line because this is a very last data point at LSB. And then index -1, because this is not inside the if statement. So this one serves all the data points. But whenever it's getting to 0, is it still doing this again or not? Yes, it is, right? But it's okay because it's going to be reset somewhere on the top to 7. So that's fine. And when stop, so it's not busy anymore, pull this up, so disable the transmission and move the state to ready again. So come back to ready again. That's the transmission for the leader. So sending data out at 2 megahertz. It's just one data point, one data line. Just keep sending data to that line. That's it. Okay. On the other side, there's a follower to receive it as well. So the follower, if the follower detects a 0 from the SS line, the enable line, do they share the same SS, follower and the leader? It's just the one line, it's just one voltage node. If the leader pull it down, the follower is going to sense it. If the leader pull it up, the follower will sense it as well. So whenever it pulls it down, the follower is going to sense it, right? So it's going to have a response here. So if it senses a 0 here, right? Then start receiving things from this data line. MOSI, they share the same voltage node. So whatever on that line is going to be stored into the data here. It's an 8-bit data. So starting with bit 7, and now it's getting busy. It's not ready for another point because it's just trying to receive the bit 7 first and move to receive. If it's receiving the very last one, which is the LSB, then just stop it, right? Or move to the stop state. Otherwise, just to keep decreasing the index, moving to the lower bit. And keep in mind, you don't have begin and end to wrap up these two lines, so which means this else only has this one line here, right? It's going to only execute the first line. So this one doesn't belong to else or if, the last one. And these are very straightforward. So you can see that the SPI is actually very simple. It's simply just to add a certain, so always add a rising edge or falling edge. So here's the falling edge. It's very interesting for the follower is that the rising edge is going to receive it. We're going to look at the table very soon, so you'll understand what's going on here, okay? But if you don't dig into the details of the code, right, just think about SPI. It's actually very simple. So the leader is sending out a data from a byte, starting with the MSB, just throwing the MSB to MOSI to the data line. That's it. And the receiver is at the rising edge and receive just assign whatever on the data line to the byte, to the MSB of the byte. That's it. Like this one is throwing and this one is receiving. But details, you have to include all the clocks and everything in there. The timing is very simple. Okay, so it's very similar. It's very similar to the very quick quiz question. Okay, I'm not showing you the details. What we just did over here. Follower, transmitter, leader, receiver. I mean for both of them. So what's the left one? Leader what? Leader what? Leader transmitter, right? Oh, leader transmitter. So the leader sending, because it's MO. So it's MOSI, right? So it's master out. So that's why it's a leader transmitter. And SI, right? So we need SI here. So on the right hand side is the SI. It's a follower receiver, follower in. So what this one should be? Leader receiver and follower transmitter, right? So for this one, for this light sensor, which one we are going to use? So if you look at the board, so the designer didn't even bother to put a input in there. Are you going to, is this one receiving anything? No. It just sends the light intensity and send it out, right? So this should be what? Should be follower. Why is a follower? Why is not a leader? Because this guy is not intelligent, doesn't have a CPU on it. It's just the SPI module, like I just said, right? This is the photodiode and send a flow current to this little chip on the module. And the chip is converting that current, photocurrent into voltage and digitize it using the ADC. And all these bytes are being sent to the SPI module and send it out from the serial port, which is SPI. So this must be a follower, and the SPI module on the chip is a what? It's a transmitter. So it's going to be SO or SI. SO, right? Then you need what? IMI, right? So we need an IMI SO for this design. So we need an IMI SO For here or for your IPGA? What you are going to design? Your task. Why not this guy? Yeah, it's already there. Already taped out. Couldn't change anything. So this guy is SO. It's a MISO for the follower. Already taped out on the chip. So you need to program a MISO for your leader, right, on the IPGA. Is this a leader's MISO? The first one I introduced? No. So it's not helpful. So you need this one, right? Left or right? Both? Which one? The right hand side, right? The left is right here. Okay. So you need a leader receiver. See? So in this drawing, the diagram, I showed you the connections, but you don't need to worry about connection because this is already on the pin header. You just plug in, it's going to make the connection. You don't need the jumping wires. And you need like 1, 2, 3, 4, 5 modules to do the job. And these modules are just not reasonable like to do it in a week. So all these modules are available on the textbook. You must be able to find the PDF version, or if you have a hard copy, that'll be even better. You just spend the time to type it in your GVM, okay, and put them together. And I believe there's a top. Is there a top? I think the first one is the top. Okay, and you have 4 modules. So what this does is, this is an 8-bit light sensor. So the binary number is going to be received by the IPGA will be from 0 to what? 8-bit. No, in decimal. So you can imagine the values are going to be 0 to what? Yes. Okay. So if you watch the demonstration here, I just turn on the flashlight of the camera on my phone. I can see it's saturating the light sensor. If I move it away, it's showing a lower value, but now it's like 250 something. Okay, it's reaching the limit. All right. So definitely it's using the 7-segment display. So that's why you need the 7-segment driver here. And binary to BCD. BCD is just binary coded just a decimal. It's just a lookup table. We convert binary to decimal. So that's why it's showing decimal number on the 7-segment display instead of binary number. It couldn't show binary there, right? You can use the LED lights to display a binary number, but for the 7-segment display, it's showing decimal numbers. So we need a converter here, and we need a leader receiver here. Leader receiver because the leader is IPGA board, and it's receiving from the follower. Okay, and need a decoder for the 7-segment display, which is converting the number to the bars on the display modules, LEDs on there. Okay. One more thing. So you are going to need a leader receiver, which is this guy. Okay. One more question. So for the SD card module you are going to use for the 351 class, you have done that before, I think. So for the 351, the ESP32 module, it receives acceleration data to the ESP32, and you'll send it to the SD card, right? It's a module, you can plug in an SD card. So if you are using a business 3 board to do the writing to the SD card, what do you need? what is the module you need for the IPGA, and what is the module do you need for the SD card. Do you need to design the SPI module for the SD card? No, it's already taped out. It's already in the SD card. We're on that. Let me see. No, it's in the SD card already. Actually, it has SPI in the SD card. The module doesn't do anything, just the voltage regulator stuff. So for the IPGA board, do you need so which one for one of the four modules do you need for the IPGA? Leader transmitter, right? It's gonna be the first one. This one. Okay. I don't have this kind of homework assignment for you guys, but you can imagine you should be able to do that. Just using this leader transmitter, maybe adjust a little bit. I don't know. Maybe just directly use it. You should be able to write digital data to the SD card after making the connection. Okay. But are you just writing to the SD card? Are you going to read from the SD card as well? You should be able to read from the SD card as well, right? It's a read and write process for the SD card. If you just read and never read it, it's not making sense. Why do you need an SD card? It's a trash can. It's a trash card. Anyway, so you need, if you want to do the write and read, you need a leader transmitter and leader receiver for IPGA to do the job. Okay. So if we look at the follower transmitter, since we didn't design, we are not going to design a follower transmitter for this guy. Okay, it's right there. But if you look at this one, it's not pulling down SS. So the follower is transmitting data to the leader, but follower is not actually pulling down SS to enable it. Why? See, it's directly sensing that, but it's not doing anything for SS. That's right. Why the designer or whoever invented SPI, do not allow the follower. So the follower is transmitting, right? But when the leader is transmitting, it does everything. It manages everything. I pull it down, I want to start doing that, then I'm going to do that. But for the follower, when the follower is transmitting, it still has to listen to the master, right? Or the leader. The leader is the leader, right? So the follower has to wait for the command from the leader in order to transmit anything. So that's why it's not pulling that down, but it's just sensing it. So the leader has to pull it down to start the communication. Okay, that's why when the leader is transmitting, SS is not being used for the transmitter whenever it's a follower, because it's done by the leader. Keep in mind. Now let's explain why it's falling edge and rising edge it's different for follower and leader. So SPI actually has 4 different modes. It's being summarized in this table here. 4 different modes. So the name of the 2 bits are, it's not 2 bits actually, it's just a code. It's not even being used on the hardware, just a code for people to understand or memorize. So 0001111, 4 different modes defines how the data is being transmitted and received. Okay, and we are not worrying about the following 3 ones, the bottom 3 ones. We are only doing the first one. And you don't have to define these 2 bits anywhere. It just depends on how you code it up. So the way we code it up here follows the first one. That's it. Keep in mind, you are not writing these 2 bits anywhere. You're looking, right? You're searching for these 2 bits in the Verilog. You won't be able to find it. It's not. It's just a code. Okay, it's not being used anywhere. It's just like an entry in the table. Okay, so this protocol defines which one. So the leader starts transmitting at the negative goes to 0, so it's a falling edge. So clock goes to 0, then the data will be available from the leader. it's a native edge. So in the Verilog code, you are using always add native edge of the SDK. Then the leader is going to place the data to the line. Okay, it's just the rules, right? Have to follow. That's it. Don't think about this complicated. And from 0 to 1 transition, which is a rising edge, 0 to 1, right? That's a rising edge. That's for follower, get the data captured. That's why, okay, that's why in here, for the leader transmitter, I have a native edge SDK. So that after that falling edge, right? So whenever it's activating the following things, it's at the falling edge. So data will be placed to the data line. However, the follower is not capturing that at all. It has to wait until the rising edge to store it into the data, the byte, to the memory. You know what I mean? That's just the rules for the first mode of operation. So native at floating edge, the leader send it out to MOSI to the data line, right? However, the follower is going to wait until it's at the rising edge. It's going to trigger all the. You can imagine there will be a lot of D flip-flops, right? It's going to trigger the flip-flop and lock it to the next stage. So if you look at the timing, it's exactly what we just talked about. Okay, the timing here, it totally makes sense. What's going on here? For SCK, for clock, okay, these are the SCKs. If you choose the first one, like 0, again, we're not writing that 0 to anywhere. It's just a code for that entry, right? When this one is 0, SCK is the top one. Okay, this is the SCK. If you choose like the second one, SCK is going to be different. So both are SCKs, depends on which one you are choosing. Depends on how you program, how you code up your Verilog. Okay, and for MSO, MOSI, okay, it is when this one is 0, so we are picking up 0 and zeros, right? So SCK is the top one, and also we are using the this mode instead of the bottom one. So you don't have to worry about the bottom one for now. So what's happening is when the data is available, we are looking at, for example, MOSI is a leader out, so leader transmitter, right? So here's the data. Here's the data. It didn't show the floating edge, but the floating edge is going to trigger it. So at the floating edge, also when SS is being put down to 0, it's going to activate the transmission. So MOSI transmitter starts here, which means whenever at the floating edge, the data will be available on the data line. However, the receiver is not capturing that yet. It's going to wait until the rising edge. If you look at the rising edge at this time, it's right in the middle of the data. Is that a good thing or bad thing? It's a good thing. You are getting a very stable data point. You want to sample at the edge, right? Because it's during the transition, sometimes it can be like 1.3 volts, assuming it's a 5 volts logic. Okay. Could you sample here? Yes. Could you sample here? Yes. You just don't want to sample at the edge, right? During the transition. So sample during the middle is very good. That's why, the mode 0, 0 is pretty good, actually. Make sense? So falling edge, make it available, but the falling edge is right at the edge, during the transition. Want to wait until the rising edge to sample it, capture it by the receiver. This can be very straightforward because the code is already provided by the textbook. As you just plug in, implement it. I don't even know if you have to debug it or not. It should be directly functioning. So it's very reasonable for a 1-week project. Just be careful about the place you want to plug it in. This is I believe this is the top of the board, and has to be the top row here. That has a GPL has 2 rows. Don't plug it to the bottom, but to the top. I can see the sensor is facing up, right? And plug it to the top. That's what you want to do. And demonstrate and post a video to the website. So that's it. I'm pretty sure you haven't finished a couple of other ones as well. Try the best because I have made everything available to you guys. So the goal for the rest of this, semester, just 1 week, the goal is finish everything. You don't have to invent or solve too many problems because you can directly copy and paste the code from the past semester. You can look up the students' code, right? Other students' code, or you actually use the script I posted to my website. Whatever you can get, right? Any resource you can get, just to make it work and post it to our website. Get a report out of it. I'm going to grade it and then give the credit on that. Okay? Any questions? Any other questions? No? Seems okay. That's the quiz. Ethics. Just 2 questions.